Hi everyone, it's Ms. Chow again, and today we're going to talk about Chapter 7, and specifically 7.1. So Chapter 7 is about reasoning, about logic and inductive and deductive reasoning, the kinds of reasonings. And the first thing we're going to start off with is inductive reasoning to find a specific term. So the chapter is about noticing patterns and drawing conclusions from those patterns. And so in math, this is called inductive reasoning. And it's characterized by drawing a general conclusion based on looking at some specific examples and recognizing a pattern. So the conjecture may or may not be true. Inductive reasoning conclusions are based on educated guesses, so they aren't necessarily evidence-based or scientifically based. I remember the one thing that comes to mind for me is I have a brother, and my brother is very bright. And my brother is also left-handed. So when I was a kid, I made the assumption or the connection that all left-handed males are very bright. So over the years, then I looked at males and I looked at if they're left-handed or right-handed, and I decided, yeah, I think that works. But I've never really tested it, so I don't know. In any case, that's sort of how it all works. So if you look down here to the first example, it says find the pattern and determine the next two equations in each pattern. So what you want to do is, so if you look at these two equations, you look at these three equations, you'll see that it's 1 times 1 equals 1, or 11 times 11 equals 121. 111 times 111 equals 12,321. So you can look and see that the numbers so you can see here these numbers are going up, right? So it's 1 and then 11 and then 111. And these numbers are also going up. And these numbers are changing. It's like with each term or each equation, you add another digit. So let's look. And so I would say, if you looked at this, you see 1,011 times 1,011 equals 1, 2, 3, 4, 3, 2, 1. Put the commas in. So that follows the pattern, and it's also true. So if you go to your calculator and you punch in the numbers, you're going to see that 1,111 times 1,111 equals 1,234,321. Okay, so let's do one more. 11,111 times 11,111 equals, and what would that equal? 1, 2, 3, 4, 5, 4, 3, 2, 1. There you have it, 123 million.4. So this is a really cool example of how you can find the pattern in a sequence or series of equations. Down here is another example. 1 plus 9 times 0 equals 1. 2 plus 9 times 1 equals 11. 3 plus 9 times 12 equals 111. So what numbers are changing? Well, the numbers that are changing are these. This is increasing. And this is changing. And I suspect we're going to add a 3. And this is also changing. So the next equation might be 4 plus 9 times 1, 2, 3 equals 1,111. And if you go to your calculator, sure enough, that's going to be true. And the next one is 5 plus 9 times 1,234. And that's going to equal 11,111. So there we have carried on that set of equations too. Now I'm going to shift over and actually go to the whiteboard because my little touchpad here is quite finicky and very messy. I'm going to go to the whiteboard where I can control better what you see and make sure you can read it. Okay, so bear with me for just a minute. Okay, I hope you can see me. I think you can. So now we are going to talk about patterns that are in series or sequence. And so the example is find the next two terms in the pattern 2, 4, 12, 48, 240. Okay, so if we look at this, we see, well, 2 to 4 is 2, so whether that's addition or multiplication, I'm not sure. And 4 goes to 12, well that's 8 for addition and 3 for multiplication. And 12 goes to 48, well that's a really big number if you add, and it's only 4 if you multiply. So what if we conjectured that 2 to 4 is times 2, 4 to 12 is times 3, 12 to 48 is times 4, 48 to 240 is times 5, and then what's the next number? Well, the next number would be, if this is 2, 3, 4, 5, the next number would be times 6, and 240 times 6 is 1440. And then if you want the next number, well, that would be times 7. And that's 10080. Okay. So you can see here how the pattern goes. So let's do another example just to make sure it's clear. Okay. Erase that. Okay, the next one is 3, 12, what's next? 13, 52, 53. Okay, what's next? Well, the first thing I noticed about this is that there's some in here, like 12 to 13, it's just adding 1. And I find that kind of unusual because normally a sequence or a series is it's the same. All the numbers, the distance between them is the same. But in this case, 3 to 12 is not 1. 3 is not 1. So let's take a good look at this and say, okay, so that's 1. So then what is the relationship between 3 and 12 that could be similar or move into 13 to 52? Well, I know 13 to 52. I know there's 52 cards in a card deck, and there's 13 cards in one of the suits. So I know that this is 4 times 4. And 3 times 4 is 12. So it looks like the pattern is multiplying by 4, adding 1, multiplying by 4, adding 1. So in that case, then the next number, what you would multiply by 4, which is 212. And then you would add 1, which is 213. And those are our next two terms. Okay, it is really my favorite sequence of all time. When I first found it, I didn't think anything of it. I thought it was kind of stupid that 5, 8, 13. That somebody could be so excited about a sequence. But then I got more comfortable with it and learned more about it. So this is 1, 1, 2, 3, 5, 8, and then I've gone on 13. So how are these numbers related? Well, the numbers are related because if you look at it closely, 2 is the sum of these two. And 3 is the sum of those two. And 5 is the sum of these two, 2 and 3. And 8 is the sum of 3 and 5. And 13 is the sum of 5 and 8. And this goes on forever. And it's called the Fibonacci sequence. And Fibonacci was a guy back in the day who identified this. But it's also got another name, because if you divide any number over the preceding number, eventually, as the numbers get larger and larger, you come to a number 1.6 and a whole bunch of numbers after that. This is like pi, where you can't, there's no end and there's no repeat. This one is called phi. And phi is used in lots of different things. So I've given you 2 videos that I'd like you to watch if you have time. The first one for sure, because it really expresses and explains the depth and the scope of the Fibonacci sequence. And the second one is more just for fun, because it shows how in music it's very, very common to see this. In fact, if you think about it, there's, what are there, 8 keys in an octave, and there's 13 keys between those two, and considering the black keys. And there's 5 black keys in between those 8 white keys. So, like, even the piano, everything has got the Fibonacci sequence in it. It's very, very, very cool. So maybe that's one thing I'll have you do for a project, is to show me something from the Fibonacci sequence, or that utilizes it. Oh my gosh, it could be anything in your garden, every flower, every seashell, everything. Alrighty, well, let's continue on. I think what I'm going to do with the next problems is I'm going to go back to my little pad, because it's easier to do these when you can actually see the design and see my writing at the same time. So here we are. The next question is, what is the pattern in the diagram below? And then what's the 15th term? What's the 20th term? And determine an equation for the nth term. So you're trying to figure out, clear up to the nth term. Okay, what color do we want? No, we don't want that. That one's good, pink. I like pink. Okay, so pattern number 1 has 4. There we go. Maybe I'll do a table over here. So I'm going to call this the term. So that's pattern number 1, number 2, number 3. And then I'm going to call this S, the number of squares. So there's 4 squares with number 1. There's 6 squares with number 2. And there's 8 squares with number 3. All right. So then maybe I'll just do a couple more here. So 4 would have, what would 4 have then? If this is the pattern, looks like you're adding 2 each time. So 4 would have 10 squares plus 2. And 5 would have, let's just do one more, 12 squares. Okay, so then if we go back to here and come up with like a blue. So if you want to make this, if you want to figure out this pattern, maybe we could think about it in terms of, let's go over here. So the first term is 4. And the second term is 4 plus 2, right? Because it's 4 plus 1, 2. And the third term is 4 plus 2 plus 2. And the fourth term is 4 plus 2 plus 2 plus 2. And the fifth term is 4. And look at how many 2's I'm putting in here. So 12 is 4 plus 2 plus 2 plus 2 plus 2. So 4 plus 8, right? And if we look at that, then we see that the number of 2's is 1 less than the term. No matter where we go. This one here is 2 2's, and it's the third term. And 1 2, and it's the second term. So if we want to look at and find the 15th term, Well, the 15th term, where's my mouse? Here it is. The 15th term is going to equal 4 plus 2 times 1 less in the number of terms. So the 15th term is actually going to be 4 plus 2 times the 14th term. And we could calculate that to be, what is that, 2832? Yep. And the 20th term is going to equal 4 plus 2 times the 19th term. Okay, so we don't go all the way to the 20th. We stop here at the 19th. And so 2 times 19 is 38 plus 4, which equals 42. So if you wanted to come up with an equation for the nth term, well, the nth term is going to be 4 plus 2 times n minus 1, because if n is 5, then there's 4 2's. If n is 4, then there's 3 2's. And so this reduces down to 4 plus 2n minus 2, which equals 2 plus 2n. Okay. Now we went a little further on that than we normally would, but that's good. Okay. The next one. Describe the pattern in the sequence below. Determine the number of squares in the 19th diagram. Determine the number of squares in the 100th diagram. So here, again, whoopsie, if we make a table of values. So this is the term, and this is the square. So term 1, 2, 3, 4, 5. And the squares, well, this term 1 has 1, and term 2 has 4, and term 3 has 9, and term 4 has 16, and term 5 has 25. Okay, so what's happening here then? This is pretty straightforward. So that means that for whatever term you have, your diagram is going to be that term squared. So if we want to find out the 19th diagram, what's that going to equal? So that is 19 squared, which is 361. And the 100th will equal 100 squared, which will equal 10,000. Good. The only other thing is for tomorrow, the homework is page 247, number 1 to 5 all. And it's just really good practice for you to do the homework. So I encourage you to do all of it if you can. And if you already know this stuff, then just do what you need to do. And if you're learning, I would encourage you to do as much as you need to do to know, to feel comfortable with everything. Alrighty, have a good day.